Hello and welcome back.
Hello. All right, welcome everybody. And we hope that you are enjoying the conference as much as we are. And remember to follow the code of conduct. We have that on the website. So if you scroll to the bottom of the website, you would find the code of conduct there. And please tweet away as you enjoy with us. We're going to invite the next speaker. All right, he's a returning speaker the second time, and he's going to be talking about something that has to do with the space. All right, $9 billion of reliability lessons from James Webb Space Telescope. So welcome Robert Barron from IBM. Thank you, Robert.
Hello, very happy to be here.
Good to have you.
Let's go to space.
Okay, shall I start? Can you see me? Okay. So let me quickly introduce myself. My name is Robert. I've been working at IBM as an SRE and service management and all those things for about 15 years now. And recently I joined the CIO office, where I'm part of an architecture group for IBM's internal systems. So all the work I've been doing for SRE for our clients, basically as a consultant and recommending to them how to be SREs, now I have to come home and show that it works inside IBM. So I'm very excited about that. I also am a member of the IBM Academy of Technology, which is a cross-IBM organization where IBMers from different business units, different ways of life, different geographies can share their knowledge and their techniques. And for me, that's sort of like having a conference like this just every few weeks within IBM. I really like, more than I like learning, I like sharing. Just three of my hobbies very quickly are photography of birds, photography of space, and something that fits in with my work, the history of space exploration. And I'm very happy about that because the history of space exploration is both part of IBM's history with the mainframes of mission control, the computers on many of the rockets and spacecraft that go into space. And it's a great platform for demonstrating site reliability engineering concepts, because this is reliability to the extreme. The $9 billion that took to invest to create the James Webb Space Telescope, if something goes wrong, if it's not reliable, then it doesn't work. We can't just deploy it again. It's not something logical, it's something physical that has to work properly. And I think there are a lot of lessons and a lot of inspirations that we can take from this work into our day-to-day lives. So I'm going to discuss the James Webb Space Telescope. And before going into the technical part of the Space Telescope, the question is, why do we need a new space telescope? We've got the Hubble Space Telescope, for example, going strong for 30 years. Why do we need something new? And the reason that we need something new is that we need new capabilities. This is a picture that Hubble takes of, these are called pillars of creation, and these are gas clouds where stars are being created. But if we take a picture in the infrared light, which is what Webb will be able to do, you can see that we're seeing through the gas clouds into the stars as they're being created. So this gives us a level, and this plays very well on two levels. From a business perspective, Webb is going to give us more capabilities, but also from a SRE perspective, this is observability, is exactly the business capability that it gives us. So it's a nice sort of play on words, as it were. So in designing Webb, we start off with the functional requirements, and we see that the functional requirements drive a lot of the non-functional requirements. For example, we start off with the fact that we want Webb to have more capacity. It has to be a more powerful, larger telescope than Hubble was. So this is a business KPI. The size of Webb is the business KPI for success. So it has to have a larger mirror. That means that we have to develop something that's larger. But now the problem is that the mirror is so large that it doesn't fit in any rocket. So it has to be broken up into pieces. This is the operational constraint, and the non-functional requirement is a foldable mirror. So I wanted to do this with Lego, but we'll have to make do with paper. This is a little model of the Ariane 5 rocket, the largest rocket available to launch something. This, by the way, is the exact same. It's an advanced model of the one that Holly was talking about in her keynote session. So this is the model, but this is the size of the telescope that we want to fit in. It doesn't fit in. What are we going to do? So the solution is to break the mirror up into small hexagons. And these hexagons can be aligned together to act as a mirror. So we've got these foldable hexagons. This is a smaller number just for illustration, but the fact is that these little hexagons fit inside the rocket in a foldable configuration like this. And I don't know how well you can see it, but I can slot these now together. These are unfolding, and we have a mirror the size that we want. So that's the first non-functional requirement we're going to talk about. The second thing is that when we talk about Webb's capability, it's not just a mirror like Hubble seeing into visible light. Webb is going to go deeper into the infrared, So we need to develop a different kind of mirror. And this mirror needs to be kept cold. Infrared, you may know, is something that everything that has heat radiates infrared light. So Webb has to be much colder than Hubble. And not just colder, but we need to be able to control the temperatures exactly, because any variation, and we're going to look at something and think, oh, this is a star, this is a galaxy. No, that's just something where on Webb itself, which is slightly colder or warmer than it should be. So that means that unlike Hubble, which orbits the Earth, Webb cannot orbit the Earth, because then it means it's going into the shadow of Earth all the time, but it needs a sunshade to protect it from the light of the sun, and it needs to be much further away from Earth than Hubble was. And here's another little model of Webb itself, and you can see this is the part that is pointing towards Earth, where we've got the controls and the antennas. This is the part that is pointing away. This is where the telescope is, and the telescope is pointing up. The light comes in through here, hits these mirrors, gets reflected into this secondary mirror over here, and back into the center where the cameras are. And this thick area here is actually a layer of sun shields which control the temperature of Webb. Okay, so let's talk about how long it takes to build a telescope like Webb. So first of all, Webb not designed in a vacuum. We started off with a series of great observatories, telescopes along the lines of Hubble, starting in 1978, and these are some of them are still in production, orbiting Earth, giving scientific value today. But in 1995, NASA started working on the initial planning for the next generation space telescope, and the assumption was that it would take about $1 billion to build a larger, more capable telescope. 2003, we start the high-level design, and they realized that it's not just scaling up Hubble. We need technological breakthroughs, the foldable mirrors that we talked about, the precise control of the temperature, the unfurling of the heat shields, and so on and so forth. So they came to the conclusion that actually not $1 billion, but $3.5 billion just to build it, and another $1 billion to operate it for 10 years. So once we finish the high-level design, we start the detailed design and the construction, and by this stage it's also given a name, the James Webb Space Telescope, and like good SREs, we test. And because we have 10 technological breakthroughs that we need to achieve, we have a lot of failures. So we retest and fail and retest and fail. And this takes a lot of time, and the project is nearly cancelled many times. And eventually, it costs $9.5 billion just to build it. And that $1 billion that we thought would be enough to operate for 10 years is only going to be enough to operate for 5 years. But at least we're able to launch it in December of last year. And we finished with this $9.5 billion. And this $1 billion is starting to pay for itself. Operations begin. And the James Webb Telescope is now, it's in the middle of deployment. It's in the middle of, if we were talking about a CI/CD pipeline, we're reaching production. We're doing the final tests before we can say that the system is working and can start giving actual scientific data. So if we look at the journey of the launch, and you can see here with my model, my paper model, I couldn't really show you the pirouettes and the ballet moves and the unfurling of the whole system. But you can see that over a period of 13 days, the telescope, like a butterfly, opens up, spreads its wings, starts reporting home, and then starts going further away from Earth till it reaches the location where it will remain for the next decade. Now, during this whole process of deployment, which has not completed yet, every time that we unfurl, every time that we open a component, every time that something moves and changes, it's a point of failure. In many of these cases, it's a single point of failure, and Webb is famous for having over 300 single points of failure during this process of 30 days, each of which has to go perfectly, each of which, if it fails, the entire telescope will not be able to function. And I thought that my talk might be just going through each and every of these points of failure and explaining to you the whys and the hows and the whats, but I thought that might be a bit boring. So we're going to do something a bit more conceptual of how we got to this point. So I could tell you each of these components, the different failures that they're in, and if someone wants an exercise, a quiz at the end, reach out to me and we'll do that. But for most of you, I think what is going to be more interesting is how did NASA reach the point where they could send $10 billion worth of satellite out into space without being able to fix anything, without being able to reach out with an astronaut to say, oh, I need to move something, I need to restart something, I need to do something manual. How can the system be completely fully automated? And can I trust that no dragons will come from outer space and do something to the telescope which will cause it to fail? So where does the trust come from? And the trust comes to a great extent from our history. NASA has been sending spacecraft into space and working with them for decades. And one of the techniques we use is redundancy. Very famously, the Voyager spacecraft, which went to Jupiter, Saturn, Uranus, and Neptune, they were twins. 2 spacecraft sent, so if there's a failure in one of them, the second one would be able to complete their mission. The same thing with the rovers on Mars. Spirit and Opportunity are twins, each of them exploring in a different way. Satellite constellations, whether GPS or communications, they work in tandem so that if a satellite fails, we still have other satellites that can cover what they're doing and give us the performance and the service that we need. But sometimes we've got a very complicated system that's so large and expensive and revolutionary that we can't build 2 of them. So in that case, we want something that can be repaired. And of course, very famously, Hubble Space Telescope was repaired multiple times, and not just repaired, but upgraded. Preventive maintenance and fixing problems were performed over the decades. And today we've got the International Space Station with half a dozen astronauts working, doing experiments, but about 50% of their time is actually toil in repairing different components of the space station. If the astronauts left the International Space Station, then in a very short period of time, it would just break down and they'd be forced to send it back down into the atmosphere to burn up. So taking these lessons of redundancy of systems, repairability of systems, but building them into the subcomponents adds all the reliability that NASA needed. When it came to the James Webb Space Telescope, redundancy was not an option because it's just too expensive. Repairability is not an option because the non-functional requirements mean that it has to fly far away from Earth, far away from the capability of any astronaut to repair it. So let's look a little bit about redundancy, and we'll take an example. The very first missions to Mars from the 60s and 70s, both the Soviet Union and the United States sent spacecraft to explore Mars in the 60s, starting off in 1960 with the Soviet Union, and where they launched 2 missions to Mars, both of which failed in the initial seconds of launch. Remember, this is the very earliest days of space exploration, and a lot of failures occur, to the point where the Soviet Union didn't even bother giving the spacecraft a name if it failed in the first half hour before the launch. Sending another one in 1962, a bit more success. The Americans sent their first system in 64, where one of them succeeded. Going forward to 1969, success from the Americans, failure from the Russians, from the Soviets, and so on. But one of the interesting things that you can see here is that redundancy was not that useful. In many cases, either all the system, or either both of them succeeded, or both of them failed. Because what happened was that the failure modes were common to both of them. If it was some computer bug or some material alloy that couldn't last for long enough, or in the case of one of the Russian missions, they just launched and there was a sandstorm on Mars when they landed, so the system failed because of the sandstorm, and it affected both of the components. So redundancy was very good, but sometimes at a system level, redundancy just doesn't solve your problem because the problem is much wider. And that happens to us as SREs as well. When we start thinking, okay, I'll have some redundancy, load balancing. If I take Kubernetes, for example, they'll say, okay, I'll have multiple pods. But what if the problem is with the DNS? Then it doesn't matter how many pods I have. What if the problem is an application bug? Then it doesn't matter how many pods I have. I need to do something more reliable than simple redundancy. Okay, in the case of Hubble, very famously, when Hubble was first launched, there was a fault in the main mirror, and we got fuzzy pictures. Astronauts came in and added this type of contact lens to Hubble to improve the quality of the picture. But Hubble was designed from the ground up as something that would be upgradable over time. This was a monolith that the Americans said, this is going to be in space for 20, 30 years, and we want to upgrade the technology as time goes by. So it was designed from the first to be easily upgraded. When it came to Webb, then this was not an option. So a lot of the, I don't want to call it shortcuts, but a lot of the capabilities that they didn't have to bother about, a lot of the reliability they didn't have to bother about in Hubble was simply not available to them for Webb, which meant that they needed to do a lot more testing to make sure that none of the problems would occur when we're talking about Webb. And for example, in the case of Webb, as I said, we don't have one mirror, but we have a series of mirrors. Then each of these little mirrors is adjustable by itself, so that if we do have a problem along the lines of Hubble, then we can use the reliability capabilities built into Webb in order to fix it, and not depend on an external astronaut coming in and fixing it. And if we see what Mike Menzel, the mission systems engineer for Webb, said about the single points of failure items, then it's just it's a numbers game. When we find a single point of failure, we treat it, we inspect it, we add more layers of testing. We add more layers of reliability to the single point of failure because we can't avoid it. Because we can never reach the point where we're going to have two of them because it's too expensive or because it's simply not available. We're not going to double the number of mirrors in the system, for example, because it's simply not possible. We don't have a rocket that's powerful enough to launch it. So what we do is just test and test and test. And if we talk about the reliability of the main mirror, so when the telescope was first launched and unfurled and we start testing the mirrors, obviously the mirrors are out of alignment because they need to be aligned in space. So this is a selfie picture showing the camera taking a picture of the mirrors themselves. You can see all the mirrors here in this array. Only one of them is properly aligned, and you can see that that's why it's lit up and the others are dark, which means that we now have to slowly and surely adjust each of these mirrors so that it works properly. This is very similar to, again, let's say in Kubernetes, we want to allocate the right amount of CPU memory resources available to each and every one of our pods, and you can consider each of these little mirrors as a pod or microservice whose job is to deliver light to the secondary mirror. Now, this begs the question, why do we only have this little selfie camera on Webb? We've all been seeing for the last years, whenever something is launched into space, there's always multiple cameras showing us the launch from the perspective of the rocket itself. When astronauts do spacewalks in the International Space Station, then we've always have 4K video showing each and every one of their actions so that we can see it on the ground. So why don't we have this level of telemetry or observability for Webb itself? And the problem here is, again, the non-functional requirements. This is the side where the camera is. Okay, it's minus 233 degrees Celsius. If we now start adding cameras that will start monitor this system, these cameras have their own heat, which means that we'll actually be disturbing the scientific instruments. If we monitor them, then we'll be disturbing them. So this is, again, what we always have the challenge of how much telemetry do I want? How much logging do I want? At some point, I'm going to be logging so much that it's going to just take up too much capacity, too many resources, and I'll be disrupting my performance. So about a month ago, they finally aligned all the mirrors together, and they got the first evaluation image showing a perfect star. All the mirrors are aligned, everything is working properly. There's still more work to do in order to improve the alignment, in order to lower the temperature of the telescope even more, to calibrate the different instruments. But already out of this this is an engineering image, but we already are getting information here. These are galaxies that are not much dimmer than anything Hubble showed us before, and people are already starting to write scientific reports based on this engineering information. So just to quickly review, what is the Webb SRE strategy? And when I looked at what Webb was doing, what the engineers at Webb were doing, I saw that there were all sorts of concepts that they were working on, like prioritizing non-functional requirements and balancing with the functional requirements that they have, identifying single points of failure, trying to reduce technical debt, learning from previous missions and making sure that these problems wouldn't recur in the new ones. A lot of these things are things that SREs want to do, but a lot of the things that they were doing were things like aim for 100% availability. Well, as SREs, we don't want to aim for 100% availability. We want the right amount of availability, and we don't want to overspend neither resources nor budget in order to get there. We don't want to embrace too many new technologies for a new product. And suddenly I realized that a lot of the lessons from Webb are what not to do. Yeah? Sometimes we do have this unique unicorn of a product, which again is one of the the United States and Europe's chief scientific endeavors of the last decade. So it does have special cases. It does have a special requirements, which we should not try to replicate. We should learn as much as possible from it. But there are some things like that we can learn not to do, like not invented here syndrome is very strong. And in the case of Webb, they had no choice because a lot of their new technologies didn't exist anywhere ever, and they were inventing these things. But we shouldn't do that. We should try to reuse as much as we can so that our new product, our next version, is as slim as possible from the perspective of unexpected surprises. We shouldn't try to have one major deployment. We should try. Webb has 5 or 6 different instruments, but they all use the same mirror. They were all launched together, but that's because it's a physical object. There was no choice. We should try to do it as simply as possible, make the deployments as small and as simple as possible. Of course, the test and test and test and test some more lesson is definitely something that we should be learning from Webb. So if I take the Webb SRE strategy and look at what should an SRE take from it, so redundancy of our systems, of our subsystems is very important, but don't mistake redundancy for reliability. If you've got a lot of redundant systems that are not reliable, it's still not going to work. Make sure that your systems are repairable, or if they're not repairable, then replaceable. So often we'd say that a monolith would be repairable and a microservice would be replaceable. And of course, reliability throughout every service is the only way that we'll be able to achieve success with this crazy world of change all the time. So this was a very, very quick inspirational session, I think, about Webb. I've got some links if you want more information, if you want to build your own model of Webb, if you want to get more information about the deployment steps and the 344 different points of failure, if you want to learn more about the mirror alignment, and if you want, these are all NASA websites. There's also the European side of Webb. Back home on Earth, IBM is also embracing space, where we've deployed an edge computer to the International Space Station. We're working on a CubeSat mission and other space tech endeavors. Personally, in the CIO office, we are hiring SREs. If you're interested, please reach out to me directly. There's also my blog, where I've got articles of this nature. Some of them I covered in the session. Some of them expand well beyond what I've spoken about. And I think I've got 2 minutes for Q&A, or am I optimistic?
Hey, Robert, thank you so much.
Thank you so much. This was very, very informative, and you gave us the history, the engineering, and the lessons of the $9 billion project. Wow. No one could have done it better.
Thank you. Thank you very much. This was very good session to deliver. I hope you enjoyed it and learned from it.
Very much.
Definitely. Yeah. So I'll hand over to Eva now.
So we already have our little pop-up that tells people to go to the quiz. So unfortunately, Robert, we don't have any time to talk about space with you, although I would love to. And I think people in the audience would as well. So,
so you've got my contact details, everyone, and just reach out.
Yes, perfect. If you need anything, if you have any questions for Robert, if you want to just tell him how awesome his talk was, then please do that. He has all of his contact information was in his slides, and also if you need anything, we will be around to help you out. And now, please, everyone, run off to the quiz, and that is happening on track 1. There will be prizes. The quiz is always tons of fun. And we will see you back here in half an hour after the quiz is done. So go over there and join it. Thank you very much. See you in a bit.
Bye-bye.